So in physics, we're going to use some things that you guys have been playing with it all your life. You know, you've been working the problem with the car. You know, if I have my little car, I'm going to do this. And we know that it's moving in a certain direction. And we know, because we've done that calculation, if my car is traveling at 35 miles an hour and we travel for 5 hours, how far do we go? We've done those problems for a long time. So don't get concerned. Oops, I got a question in the chat. Hang on just a second. Okay, somebody's got questions for chapter 1 homework. We'll come back to those. Okay. So I've got my motion in my car, and we've done that problem a long time. So let's talk about the concept of displacement. So if I'm walking or I'm working on moving down the road, I have some origin here. And I'm going to move away from the origin, and I'm going to end up at some final place. And that is our idea of displacement. So we actually talk about the change in x, or our change in position, is equal to our final position, which we're going to use an f, and minus our initial position. So if we're looking at displacement, there's my origin, there's my final position. This is something that we've all dealt with. This gives us our initial position. You may also see it written as x sub I, which might be an initial position. Using subscripts on our variables helps us to keep track of things. But let's think of a swimmer. So if I'm in a swimming pool here, so my swimmer goes from here, goes and touches the pool, comes back here, and now I'm at my starting point. My change in position, or my displacement, is equal to my final position minus my initial position, which is equal to 0. Because I've started the same place and I've ended up the same place. Now, the interesting thing here, if I've got my swimmer, right? If I've got my swimmer, I'm now going to have a difference between velocity and speed. So if this pool is 50 meters long, and our swimmer, we'll say, is a slow swimmer, it's me in the pool, and I'm going in and I'm swimming in the pool, I do that in, let's go ahead and say it takes me 20 seconds to do this trip around there. I have velocity and I have speed. I also have distance traveled. Now, in this case, distance traveled and displacement is the same. But in this case, distance traveled and displacement is not the same. Displacement is equal to 0, but my distance traveled is equal to 100 meters. And if I calculate the average speed, because we said it took 20 seconds, I'm going to get 100 meters divided by 20 seconds. And that's going to be 5 meters per second. And that's my average speed. But my velocity is not that, because we're going to define velocity, and I'm going to use three little lines here. That gives us our definition. My change in my velocity is a change in position divided by a change in time. So my average velocity for this situation is going to be 0. So this is a different way of interpreting how we, or it's actually not a different way of interpreting how we've dealt with motion. It's just a way of discussing how we've dealt with motion, and we're being very precise with our words. And the reason we're being very precise with our words is because displacement is a vector. And we're going to represent it by using a vector symbol. Velocity is a vector, but speed is not. And a vector has direction and magnitude. So vectors have direction and magnitude, and speed does not have, in this case, speed doesn't have direction. But my velocity and displacement have direction, and those are going to be vector quantities. So vector quantities are going to be things like displacement, velocity, force, acceleration. All of those things are going to have direction and magnitude. So we can look at velocity. So we can look at velocity here, and we've already defined velocity. Velocity is defined as that change in position with respect to time. And this can be an average velocity. And when we talk about an average velocity, I can represent with my vector symbol, and we can put a line across the top. Typically, we're not going to do that, but we can do that. And then I can also do an instantaneous velocity. And you can think about an instantaneous velocity. It'd be whatever you're reading on your speedometer in your car. Or you can look at it like this. So I'm doing a position versus time plot. And I may be going, okay, I'm trudging along, I'm doing this, and then I may do something like this, and then I may do something like that. And we can do that tangent to the curve that you used to do in algebra. This gives me an instantaneous velocity. And if I have a straight line here, the slope is my change in position. My right, or over here is my change in time. And on a straight line, that's going to be a constant velocity. Now, in the slide deck that I've provided you, we go through this in a lot more detail that we're looking at it. But these are some of the key points that when you go through those other videos, I want you to kind of focus in on instantaneous velocity. And if you ever get to calculus or you start looking at a calculus, this refers to the limit as my time approaches zero. But it's also a graphical representation that we see on the chart. So straight line on a position versus time plot says we're traveling at a constant velocity. And I can rewrite this. So now I have an equation, and we get our first equation. I'm looking at velocity, which is a vector, is going to equal my change in position, which is also a vector with respect to time. And I can rewrite this as velocity is equal to my final position, my initial position divided by my time final minus my time initial. And if usually we start at time initial being 0, right? Then I can do velocity times time is equal to my change in position. And if that is equal to 0, I get x is equal to velocity times time. And this is when there is no acceleration. So we got our first equation. Okay, our first item in the toolkit. Well, now let's take it one step further. So now what happens if I'm going to define acceleration as a change in velocity with respect to time? I can do a plot of velocity versus time. And if I get a straight line on that plot, if I get a straight line on a velocity versus time plot, that says I have a constant acceleration. And we're going to be nice to you in general physics, and we're only going to work with constant accelerations. We're like, we'll have to calculate an acceleration, but we're only going to work with constant accelerations. We're going to make a constant acceleration assumption, but we live in a world with a constant acceleration, and that constant acceleration that we live with is the acceleration due to gravity. And so that constant acceleration that we have, that we live with it and we can work with it there. So I can do the same thing that I've done before. I can get an instantaneous one. So if I had a velocity versus time plot that did something weird, I could do a slope of my line, and this would give me an instantaneous acceleration. So I would have that instantaneous acceleration, but now I have an equation that looks like that. So let's look at that one. So I'm going to do acceleration. We usually use an A, or we're going to use a G with a script for when we're dealing with gravity, and we're going to use the magnitude. And if I do this, okay, so let me do that again. If I do this, that is going to be a positive number, and that's meters per second squared. If I look at these units here, this is where we're going to get that. I get meters per second divided by seconds, and I get meters per second squared. But my magnitude of G, we're going to use is 9.81. And when you guys start doing your experiments, you're going to find out that in Stillwater and in Enid and in Tonkawa, it's probably closer to 9.79 meters per second squared. But the constant that we utilize for physics problems is 9.81. But now we've got our acceleration is our change in velocity with respect to time. And that's going to be our final velocity minus our initial velocity divided by our final time minus our initial time. And typically we start at time is equal to 0. So if I do that, I'm going to get acceleration times time is equal to final velocity minus my initial velocity. Or I can rewrite this as final velocity is equal to initial velocity plus my acceleration times time. So there is one of our equations. And you can go in and look at that one slide deck, and you can look at the other videos, but you're going to see that we get 3 equations that we're now putting into our toolkit. One is my change in position is going to equal my initial velocity times time plus 1/2 the acceleration times time squared. And if acceleration is equal to 0, this just becomes my change in position is equal to my initial velocity times time, which is what we just started with just a second ago. So that's one equation that we use. We just did the other one. My final velocity is equal to my initial velocity plus my acceleration times time. And that's my second one. And if I have those two, now one of the things here, I want you to look at this. This has the variable of position, acceleration, and time. This one has the variable of velocity, acceleration, and time. And we're going to get a third equation that's going to use final velocity squared is equal to the initial velocity squared plus 2 times my acceleration times my change in position. And now this one is in velocity, position, and acceleration. There's no time in this one. So when we're always talking about which equation do I use, you want to look at the variables that you have. You want to look at the individual variables that you've got. Okay, that's going to help you decide which equations you're going to use. So let's do just a quick example here. Other thing I want to do is that now this X, we happen to use that X. So let's talk about our coordinate system here. Most of the time we use X to be going this way, and we use Y to be up and down if we're in 2 dimensions. We use Z if we're in 3 dimensions. Z is up. Y is, this is X, and that's Y. We use that. And if I'm doing a vector, I can have my vector, and we'll talk more about this next week, but my vector can be represented by its X and Y coordinates. And if I am denoting a position out here, I can have an angle, and I can actually write this line in terms of its X and Y components. And we'll talk more about that next week. Right now, we're only working in 1 dimension, but I wanted you to see where we're going to start getting that vector notation coming through. So I could rewrite this in terms of a change in Y, for example, is equal to this. All right, so I can say Y, X is just my position. So I could talk about shifting my coordinate system to do that. I can also, if it makes sense, I could say height is equal to this. Okay, and we're going to work a problem where I am going to use that as height. So remember, when we're just trying to give physical meaning to the variables that we've put into our equations. We're just trying to make this mathematics into something in the real world. Or we're trying to represent something in the real world by a mathematical equation. And that's what physics does. Physics is going to tie that math back to what it is we're working with. So let's do this. So we've done this before. So I'm at a stop sign. I think I can squeeze it on this page without too much. So I've got my stop sign here. And we've got our little car, right? And we know that we're going to travel. We know that we're going to travel, 50 meters. And we're starting at an initial velocity equal to 0. And we know at 50 meters, our final velocity is going to be at about 20 meters per second. 27 as a frame of reference for you, 27 meters per second is approximately 60 miles per hour. All right. So think about this car having been on the on-ramp, where they started at a stoplight and now we have to proceed to get into traffic. And we're going to go to 20 meters per second. I want to know the acceleration that I have to do for the car, and I want to know the time, because that's what we ask. We want to know acceleration and we want to know time. So what I've got here is I've got my initial velocity and I've got my final velocity, and I have my change in position. So if I do this equation, I have my velocity, I have my change in position, and this is what I'm trying to solve for. So I can use that equation. So I'm going to do 20 meters per second squared. My initial velocity was 0 times 2 times my acceleration times 50 meters. Well, 2 times 50 is 100. So now I get 20 meters per second, and that's squared divided by 100. Now I can do that calculation, and I'm going to end up with meters squared second squared divided by meters. Those will cancel, so I'm in meters per second squared, which is an acceleration. That's all good. So I'm going to do my 220. I'm going to square it. I'm going to divide it by 100. And so my acceleration is 4 meters per second squared. Well, now I know acceleration, so I can do this. So this is the other variable I'm trying to solve for. So I solved for acceleration. Now I can solve for time. We know that's 20 meters per second. It's equal to 0 plus 4 meters per second squared times time. So I'm going to do my 20 meters divided by 4. Time is going to end up being 5 seconds. So you can utilize those equations to get there. So we've got a lot of powerful equations. And with physics, it's practice, practice, practice. It's looking at your problem and it's solving problems. So we're about to take one and do it a little bigger. So I'm gonna actually stop here for a second.